Okay, so welcome back to this next video in which we are discussing entropy and the second law of thermodynamics. Okay, so we were just discussing the combustion of magnesium. Okay, so we were discussing how magnesium as a solid, so a metal strip of magnesium, can react with oxygen in a combustion reaction, and two magnesium atoms will react with an oxygen molecule, and what they will create is the ionic compound magnesium oxide, which contains a magnesium 2+ cation, okay, so a divalent cation of magnesium bound to an oxygen anion here. Okay, so an oxygen 2-, like so. So the magnesium atom has given its outer two electrons to the oxygen atom to create this ionic compound here, and you'll clearly create two magnesium oxide molecules, and these are also a solid. Okay, so this is magnesium oxide. Right, so again this reaction goes to completion. So if you react magnesium with oxygen, all of the magnesium atoms will end up reacting with the oxygen molecules, and you don't get any reverse reaction occurring. Okay, so what we now want to do is try and develop a basic theory for why. Why does the chemical reaction go in one direction and not the other? Well, one thing that you might think is that maybe the energy of the products is lower in both of these cases, and indeed it is. If we look at energy diagrams, okay, so let's have a look at this. So for instance, if we do this reaction where we've got magnesium reacting with oxygen, if we look at the reactants on one side, so we take the two magnesium ions plus an oxygen molecule, and we look at how much potential energy is stored within the structure of these molecules. Then, if we look at the potential energy stored within the two magnesium oxide molecules, okay, we find that the energy in this structure is lower than the energy in this structure. So when you go from this to this, what happens is energy is going to be released from the reaction, and this will be released in the form of heat. So basically, if this reaction occurs, you'll find that it gives out heat, basically, and obviously that fits with normal experience. We imagine, if you burn magnesium, it's going to release heat. Now, the fancy name for a reaction that releases heat is that it is exothermic. Okay, now if we discuss the other example that we looked at, which is when we take ammonia as a gas and react it with hydrogen chloride as a gas, okay, and what we get is ammonium chloride, which is a white solid, okay. Then basically, again, if we draw one of these energy diagrams where we plot energy on the y-axis and then the x-axis doesn't really show anything, okay, so this is just energy here, so you only really need one axis, and then we look at what the energy of the reactants was. So if we add up all the energy stored in the structure of ammonia and all the potential energy stored in the structure of hydrogen chloride, okay, then basically we find that that is greater than the amount of energy in this product, ammonium chloride. Okay, so again, what has happened is when this reaction occurs, every time it occurs, energy is being released. So the reaction is exothermic. It's releasing heat, basically. Okay, so that might lead us to hypothesize then that a chemical reaction will occur if it releases energy in the process, i.e. if the energy, the potential energy of the products is lower than the potential energy of the reactants. Okay, so there's our theory. Now, often people use the term stable, okay? So people will say that ammonium chloride is more stable than ammonia and hydrogen chloride. So the products are more stable than the reactants. And what they mean by that is they mean has a lower potential energy. Okay? So if something's more stable than something else, it means it has a lower potential energy. Okay, right. So That's what is meant by when people use stable. It's kind of like a colloquial term, but this is what it sort of is meant to mean, has a lower potential energy. Okay, right. So there's our theory at the moment, that chemical reactions will occur if the products have a lower energy than the reactants, i.e. if the products are more stable than the reactants. But what we're going to do now is we're going to blow this up. It's not right. At the very best, it's oversimplified, if not completely wrong, basically. It doesn't work. And how can we see that it doesn't work? Well, we can find a counterexample that it can't explain, basically. So that will show us that we need to go back to the drawing board, we need to rewrite our theory because it can't be right, it disagrees with reality. Okay, so a really simple example is you can take the product of this reaction, ammonium chloride, and you can leave it at room temperature and it will absolutely not return back into ammonia and hydrogen chloride. Now that's perfectly in agreement with our current theory that it will only proceed if it's going to result in products that have a lower energy than the reactants. And of course, ammonium chloride has lower energy than ammonia and hydrogen chloride, so you won't find it splitting back into the other. However, what happens if you heat ammonium chloride up? So let's now get our Bunsen burner out and heat ammonium chloride up. Basically, if you heat ammonium chloride up, this white solid, you can actually make it split back into ammonia and hydrogen chloride. So you can get this reaction to occur if you heat the reaction up. It won't occur at room temperature, but if you apply heat, okay, this can occur. So that blows up our theory. We said chemical reactions can only occur if they result in products which have a lower energy than the reactants. Here, we've just changed the temperature at which we're doing the reaction, and suddenly we can get a reaction to occur where the products now have a higher energy than the reactants. Now, such a reaction where the products absorb energy, basically, you have to put in heat to make the reaction go, is called endothermic. So when the energy of the products is higher than the energy of the reactants, it's called an endothermic reaction. Okay, so we found an endothermic reaction, basically, and this blatantly contradicts our theory that reactions will only occur if they release energy, basically, if the products have a lower potential energy than the reactants. Okay, so that theory has blown, but before we actually see the solution of it, I'm going to show you more about how wrong it is, basically. Okay, and we're also going to see how it's wrong with an example of an equilibrium, basically. We're going to see a reversible reaction, okay, and this will also demonstrate how this theory is clearly not correct. Alright, so the example of the reversible reaction that we're going to use is the dimerization of nitrogen dioxide. Okay, so the dimerization of nitrogen dioxide involves two molecules of nitrogen dioxide, which is a gas, okay, and basically what can happen is they can bind together, okay, and to understand this I need to show you the structure of nitrogen dioxide. Okay, so nitrogen dioxide consists of a nitrogen atom and it's double bound to an oxygen atom, and it's also got a single bond to an oxygen atom. Now basically that means that this oxygen atom is not happy, because oxygen needs two bonds, basically. So let's draw out the electrons, the outer shell electrons for this oxygen atom. Let's do them as crosses, and then we'll have the dots for the nitrogen atom. So oxygen has 6 outer shell electrons, so the other 5 will now be 4 of them will be in lone pairs, like so, but then another one will be all on its own, so it's not happy, basically. This is extremely unhappy, and it is extremely reactive. And what actually happens is that this oxygen atom nicks one of the electrons that is in the nitrogen's lone pair. So nitrogen also usually has a lone pair, okay, but what's going to happen is one of those electrons is going to get nicked off the nitrogen and will end up bound to within the oxygen, okay, in a lone pair with one of the oxygen's electrons. So the oxygen gains a negative charge, but it no longer has a free radical. The poor old nitrogen gains a positive charge, and it also now has an unpaired electron, because that one that I've blacked out is no longer there. So it's also a free radical. So basically, this is the structure of nitrogen dioxide. You have nitrogen double bound to oxygen, and this nitrogen has a positive charge and an unpaired electron, a free radical. This oxygen down here has a negative charge but no free radical. Okay, so what can happen is you can bring along another one of these nitrogen dioxide molecules here, like so, and basically they can bind their two lone electrons together to make a covalent bond between the two, and they'll both have a positive charge. And this structure is then called nitrogen tetraoxide. Okay, so this is nitrogen tetra, meaning 4, and then we've got 4 oxygen atoms, so it's tetraoxide. So what can happen is the two nitrogen dioxide molecules, which are a gas, can combine together to make N2O4, nitrogen dioxide, which is also a gas. Now, basically, this reaction is, this forward reaction, when you go from nitrogen dioxide to nitrogen tetraoxide, this is an exothermic reaction. It releases heat. So if we look at the energy diagram for this reaction, then what we find is that two nitrogen dioxide molecules have a higher potential energy than does a nitrogen dioxide molecule, dinitrogen tetraoxide molecule down here. Okay, so the forward reaction releases energy. Okay, so you might expect that if you get a chamber of nitrogen dioxide, you fill up a, let's say, a glass container here. So we've got this glass box, and we fill this glass box up with nitrogen dioxide molecules. You might expect that absolutely every single one of them would react to make nitrogen tetraoxide, because it's an exothermic reaction. It releases energy. If our previous theory was right, then yes, if you leave it for a long enough time, every single nitrogen dioxide molecule will react to produce nitrogen tetraoxide molecules. Okay, if you've got an odd number of molecules, then not absolutely everyone will react. But of course, in reality, not absolutely everyone will react anyway. Every single one of them will react to the point that only a trivial few have not reacted, basically. So the number that haven't reacted are negligible and potentially unmeasurable. Okay, so that is not what is seen, basically. Instead, what you find consistently is that if you do this experiment at normal temperature and at normal atmospheric pressure, you find that 70% of the nitrogen dioxide molecules combine together to make nitrogen tetraoxide. So let's try and show 70% of this container. So around that many. So this many will combine together to make nitrogen tetraoxide, but the others will remain as nitrogen dioxide molecules. And that's consistent. It doesn't matter how long you wait, basically. It remains as that. Okay, so what we now know is that actually it forms a dynamic equilibrium. Okay, so the nitrogen tetraoxide molecules can actually turn back into nitrogen dioxide molecules. They can split apart again and return back to the nitrogen dioxide molecules. And the equilibrium point, okay, which is a dynamic equilibrium, that's a good term. Okay, this is the point where the rate at which you are forming nitrogen dioxide molecules is equal to the rate at which they are breaking apart. Okay, so at this equilibrium point, you've got a whole bunch of nitrogen dioxide molecules, and I should stress that they're not just going to be all at the top here, they're all going to be mixed together. So 30% of the nitrogen dioxide molecules will still be free, and the other 70% will be in the nitrogen tetraoxide molecules. Okay, now that 30% that are still free, they will be reacting together and making new nitrogen tetraoxide molecules. So in a certain amount of time, let's say a second, you will be getting a certain number of new nitrogen tetraoxide molecules being made. So let's say you make, just for argument's sake, and this is a far too small number, but just for argument's sake, let's say that you make 1,000 new nitrogen tetraoxide molecules in a second, okay, in 1 second. Basically, at the point where there are 70% of the nitrogen dioxide molecules present as nitrogen tetraoxide, the number of nitrogen tetraoxide molecules which happen to break apart in a second and return to nitrogen dioxide molecules will be the same number. So you'll also get 1,000 well, I have to be more careful now. You will also get 500 nitrogen tetraoxide molecules breaking down to become 2 nitrogen dioxide molecules. Therefore, you will also get 1,000 nitrogen dioxide molecules being released, basically. And I think I might have... Right, okay, let me just re-say this because I didn't foresee the complication with having to halve it. Okay, so, basically, let's say you take 1,000 nitrogen dioxide molecules and they'll combine into nitrogen tetraoxide molecules to create 500 new nitrogen tetraoxide molecules, and that happens every every second when 30% of the chamber are nitrogen dioxide molecules. And then when 70% of them are dinitrogen tetraoxide molecules, then you'll also get 500 of these breaking down to release 1,000 new nitrogen dioxide molecules. So the rate of the forward and backward reactions are the same at that equilibrium point, basically. That's why it's called a dynamic equilibrium. Because even though it looks as though the macroscopic variables, which are the concentration of each of these forms of the nitrogen dioxide molecules in the container, are constant, in reality it's not just fixed, basically. There are loads of microscopic procedures still going on. So even though the macroscopic picture isn't changing, the microscopic picture is extremely dynamic. That's why it's called the dynamic equilibrium. Okay, so basically this shows us, well, the fact that it doesn't go to the point where all of these molecules are actually dinitrogen tetraoxide molecules shows us that there must be a reverse reaction. How else could it possibly occur? If there was only the forward reaction, then you would assume that eventually all the nitrogen dioxide molecules would collide with each other and would be converted into nitrogen tetraoxide molecules. The only possible explanation is that the nitrogen tetraoxide also can break down, basically, and that's in contradiction to our hypothesis that only reactions which result in products of a lower energy than the reactants can actually proceed, because the nitrogen dioxide molecules have a higher energy than the dinitrogen tetraoxide molecules. Okay, and indeed what you can find out, well, what you can do is you can actually show that you can make both exothermic and endothermic reactions go. So you can do an experiment to show this. Okay, so let me get another piece of paper to show this. So basically this is the experiment that you can do to show this. Basically, you can start off with a container that contains completely nitrogen dioxide molecules, i.e. contains absolutely no dinitrogen tetraoxide molecules. Now, how can you do that? Well, if you take the container to very, very low pressures, okay, so you pull this plunger right out so that the pressure of the container, the pressure of the gas within the container is extremely low, then that favours all of the nitrogen dioxide molecules being free. Okay, so most of the molecules will now be free rather than paired up in dinitrogen tetraoxide. Okay, so this is at extremely low pressure. Okay, in addition, you can start from all dinitrogen tetraoxide molecules. Now it's the exact reverse condition this time. You start at extremely high pressure, and this forces all the nitrogen dioxide molecules to pair up as dinitrogen tetraoxide molecules. Okay, so this is extremely high pressure. So we have the same number of, let's say, nitrogen dioxide molecules in each of them. Okay, so here they're all paired up, but let's say this the same number in both. Okay, except that here they're not paired up and here they are. And basically what we're going to do now is take it to normal atmospheric pressure. Okay, so we're going to move the plunger into the middle now. And this is, let's say, 1 atmosphere pressure, so that's the normal atmospheric pressure. And what, of course, will happen is it will reach this equilibrium where 70% of the nitrogen dioxide molecules are present as dinitrogen tetraoxide, and the other 30% are present as free nitrogen dioxide molecules. Okay, and basically it will form this equilibrium whether you start from the low pressure here and push the plunger in to increase the pressure to 1 atmosphere. Okay, and of course we would have predicted that with our initial hypothesis. We would have predicted that the nitrogen dioxide molecules would then become dinitrogen tetraoxide molecules, because the dinitrogen tetraoxide has a lower potential energy. Okay, so this is the exothermic reaction, so you can get to the equilibrium via the exothermic reaction. However, if you pull the plunger out, you can also make it go to this. Okay, so you can make the dinitrogen tetraoxide molecules break apart into 2 nitrogen dioxide molecules. Okay, and that we know is an endothermic reaction. So you must be putting heat into the dinitrogen tetraoxide molecules for that to occur. Okay, so you start with a container with purely dinitrogen tetraoxide molecules, and you can turn it into this basically. So that clearly contradicts the theory that only chemical reactions which result in products which have a lower energy than the reactants can occur. Okay, so in the next video what we'll do is repair this mess basically. We'll come up with a new theory.